Today we will talk about the Zener Diode. Voltage regulation means stabilizing the voltage in a circuit and eliminating the effects of voltage fluctuations. As shown in the diagram, this is a voltage regulation circuit built with a Zener Diode. When the input voltage changes, the output voltage remains stable. How is this voltage regulation achieved? One key component is the Zener Diode. Its English name is Zener, which is transliterated as Kina diode in Chinese. When discussing the VI characteristics of diodes earlier, we mentioned that reverse breakdown in ordinary diodes is irreversible. Once breakdown occurs, the current increases sharply like an avalanche. This causes permanent damage to the diode. However, there is an exception, the Zener Diode. Its reverse breakdown is reversible. After breakdown, it is not damaged and can operate stably in that state. Let us look at the characteristic curve under reverse breakdown. In the breakdown region, the VI curve is nearly a vertical line. This means that no matter how the operating point changes, it remains constrained by this curve. The voltage on the horizontal axis is therefore a constant value. By connecting such a Zener diode in parallel in a circuit, a stable voltage can be obtained. For example, in a resistor voltage divider learned in middle school physics, when the supply voltage changes, all node voltages change accordingly. But if a Zener diode is connected in parallel, the voltage at that node is clamped to a fixed value. For example, in a practical circuit, we may need a stable 3.3 volt supply. We can choose a Zener diode with a model N4728. Its first parameter, the Zener voltage is 3.3 volts. Then a standard regulator circuit built with it can output a stable 3.3 volts voltage. Other Zener diodes in the N47 series offer different regulated voltages such as 3, 3V, 4, 7V, and 5.1 volts. The second parameter of a Zener diode is the rated power ZIM. It represents the maximum power the diode can handle. Its value equals the Zener voltage US multiplied by the maximum current ISM. Thus, the maximum current ISM can be calculated. In practical circuits, to prevent overload damage to the Zener diode, its operating current must be limited. This is usually done by adding a series current limiting resistor. The following formula is used to calculate the minimum resistor value. This is an important step in regulator circuit design. The third parameter of the Zener diode is the rated current is. It is the minimum current required for regulation. Only above this value can good regulation be achieved. Therefore, the current limiting resistor cannot be too large. The following formula is used to calculate the maximum resistor value. In real regulator circuits, the resistor value should fall between the calculated minimum and maximum. A reasonable safety margin is sufficient. Other Zener diode parameters such as dynamic resistance Rs and temperature coefficient CTV can be selected according to requirements and datasheets. When Zener diodes are used for power supply or protection, there are usually no special requirements. When used as a voltage reference for precision instruments, higher performance parameters are required. With technological development, many chip-level voltage regulators have emerged. Examples include voltage reference sources such as LM399 and LTZ1000. They offer much higher voltage stability. Even when ambient temperature changes significantly, the output voltage remains stable. Inside these precision regulator chips, the key element is still the Zener diode we are already familiar with.